Alright, ladies and gentlemen, in this video we're looking at section 5.3, dealing with what's called the divergence test and a second test called the integral test. The first test, the divergence test, is going to be a simple test that uses the limit process to inform us about the behavior of certain series. The second test, the integral test, is going to allow us to rephrase the concept of the convergence or the divergence of a series into a question about an improper integral. And since we've studied those improper integrals already, and we've developed some basic techniques, we'll be able to use those techniques to actually analyze certain series as well. Okay? So let's start with the divergence test. This is a very simple test, but it's often misunderstood by students. So we need to understand how this works from a logic point of view. The divergence test really relies on the fact of this. Note, if an infinite series converges, then it must be true that the limit as n goes to infinity of those terms you're adding up is 0. In other words, think of it this way. If I was to keep adding things that were not 0 forever, certainly that would not be a finite value. So if this is going to be finite as an infinite sum, it must be the case that these terms go to 0 in limit. So, logically, as a consequence of that, if the limit of the terms is not 0, this series cannot converge, and that's what the divergence test says. If the limit as n goes to infinity of a sub n is not 0, then this infinite series diverges. So this is a test you can use. Simply taking the limit of the terms of your series, if those terms do not go to 0, you're done. You know that the series diverges. Now, you have to think about the logic of what this says. This says you can reach a conclusion if the limit of a sub n is not 0. Then we know something. If this limit of a sub n equals 0, then the test is inconclusive. So be careful. If the limit as n goes to infinity of a sub n equals 0, we can make no conclusion. Okay? This test does not tell you anything if the limit equals 0. All right. Now, the second test, the integral test, is going to be a lot more work for us. Okay? What this says is if you're given an infinite series such that these terms that you're adding up are positive, okay? If you can do the following, if you can find f sub x such that when evaluated at the ends, you get back a sub n. So it matches up with this generating function for the series. And f is continuous over the interval, in this case from 1 to infinity. F is decreasing over the interval from 1 to infinity. Then, and this is why it's called the integral test, we can test the convergence of this series by looking at the convergence of an equivalent improper integral. This improper integral and the series we started with both have the same behavior. They either both converge or both diverge. So of course what that means is that you're just rephrasing the question about this infinite series into a question about an improper integral instead. And of course the reason we want to do that is because we know techniques of integration to analyze this improper integral. Now, the classic example of a series that we apply this test to is the P series. So definition. The P series is this. Okay. We have already looked at the P series a bit. For example, note, if P is equal to 1, that's 1 over n to the 1. That is, the P series is the harmonic series. Which of course diverges. And since we know the harmonic series diverges, we know when P is 1, this diverges. We don't have to do any other analysis in the case that P is equal to 1. But what about the cases where P is not equal to 1? Okay. Well, then let's take a look at the integral test and see if we can apply it. This would be the function that we would use to replace 1 over n to the p. This is, in other words, the continuous version of this generating function for the series. Okay. And what do I need to know about this? Well, of course, I needed to know that this was positive, and it is over the interval from 1 to infinity. That's positive. Therefore, I look and say, is this function continuous? Yes, it's continuous on the interval from 1 to infinity. Is it decreasing? It's very simple to see that as x gets larger and larger, this is going to be decreasing on the interval from 1 to infinity, of course, provided that that p is a positive value. If p were negative, that would throw this up into the numerator, and this would not be decreasing. Okay? So that's true for p positive. All right? So what that means then is I am able, because I have satisfied these conditions for this positive term, represented as this continuous version of it, what I am able to do is analyze the behavior of this series by looking at the behavior of the improper integral from 1 to infinity of this function instead. Okay? And so that's what we do now. We say the behavior of that improper integral is going to tell us what the series is going to do. Okay? All right, now how do I calculate this improper integral? Well, you know that since it's improper, you're supposed to represent it as a limit process. The limit is b goes to infinity from 1 to b of 1 over x to the p. I'll write that as x to the negative p. All right, so that's a simple power function. We know for sure p is not 1, because if p were 1, this would be the harmonic series, and we would not be using this test. So p is not 1, so that means I'm going to analyze this by using the integration of a power function. So I add 1 to the power and divide by the new power to get the integral calculated. Okay, so adding 1 to the new power and dividing by it, I get that. Adding 1 to the power, I get that. Okay? All right, now, to analyze this limit, let me take this into the denominator. Okay? So this x to the negative p plus 1, I want it in the denominator. And the way I do that, of course, is to negate its power. So negative p plus 1 negated becomes p minus 1. Okay? All right. Now, what does this equal in limit? Well, it really comes down to what the value of p is that determines whether this limit exists or not. If the value of p is bigger than 1, if p is bigger than 1, then this is a positive power. And this infinity, therefore, stays in the denominator, driving everything to 0. And so we would say the improper integral converges. If p is less than 1, then this power, if p is less than 1, is negative, pops this infinity into the numerator and gives you an infinite limit. Okay? Recall, we already handled the case when p was 1. We know divergence when p was 1. So what we conclude here is the series from 1 to infinity, 1 over x to the p, converges for p bigger than 1 and diverges for p less than or equal to 1. And there we have our complete analysis of what a p-series does. We understand how all p-series work now because we've analyzed their powers. Okay? All right, so that's how the integral test works, and we'll do a few examples from the exercises in just a minute. But I want to point out one more thing we can do with this integral test. We can talk about the remainder estimate. Process from the integral test. And so this is how the remainder estimate process will go. Okay, we want to estimate. We want to estimate the sum of a series from 1 to infinity by a partial sum. Say S sub n is the sum from 1 to capital N. Okay? And I want to know how far off that is from the infinite sum. That's what we mean to try to estimate this. Okay? And so what we notice this, that partial sum plus the improper integral from n plus 1 to infinity of the continuous version of this by the integral test is less than or equal to the infinite sum that we're trying to estimate, which is less than or equal to the partial sum plus the improper integral from n to infinity. In other words, the error or remainder R sub n is such that it's bounded between these two integrals. And so we can use this integral to estimate the error that we could possibly have when calculating one of these. Okay? All right. Now let's turn our attention to the exercises and crank through some of those to see how we use the divergence test, how we use the integral test, and then I'll do one example, I believe, with the remainder estimate process from the integral test. All right, so let's take a look at problem number 138. And these first ones are going to go very quickly. They're simple problems. You're given a sub n is n over n plus 2. And you're asked for the series that is, of course, summing this from 1 to infinity apply the divergence test and determine whether that series converges or not, if possible. And if the divergence test doesn't apply, tell me why. All right, now, to apply the divergence test, you simply take the limit as n goes to infinity of this term. As n goes to infinity, n over n plus 2 looks like n over n, which is 1, and so the limit is 1. In order for this to converge, it must have been the case that the limit was 0. So since the limit is not 0, we have divergence. In other words, this eventually looks like you're adding 1 plus itself forever when n is really large. Okay, and that's how the divergence test works. If the limit is not 0, you have divergence. Let's look at 140. In 140, a sub n is n in the numerator, in the denominator the square root of 3n squared plus 2n plus 1. So you simply say the limit as n goes to infinity of n over the square root of 3n squared plus 2n plus 1. And to take the limit of this, you throw away the lower ordered terms in the bottom. This looks like n over the square root of 3n squared. Well, the square root of n squared and n cancels, so you're taking the limit of 1 over the square root of 3. That's not 0, so you have diverges. All right, let's take a look at number 142. In 142, a sub n is in the top 2n plus 1 to the 2n power, and in the bottom 3n squared plus 1 to the n. And of course you need to take the limit of this. Now, before I go ahead and take the limit of this, let me suggest you can rewrite this to make it more easy to understand. Okay? 2n to the plus 1 to the 2n power can be thought of as 2n plus 1 squared, all raised to the nth power. Now square out the 2n plus 1. You get 4n squared plus 4n plus 1 to the n, 3n squared plus 1 to the n. In other words, you've got 4n squared plus 4n plus 1 over 3n squared plus 1, all raised to the nth power. And I'm trying to take the limit of this. Okay? Now, when you have this term n up in the power, and you're taking the limit as n goes to infinity, we're going to use a little trick to help us with that. We say, let's give this limit a name, call it L. And of course we want to find the value of L. Well, to get that n out of the power, simply take the natural log of both sides. By taking the natural log, that allows this n to come down in front as a coefficient. It also allows you to pass the log inside the limit. That's what we do first, actually. Now I'll take this down in front. Now, to compute this limit, let's see what we've got here. N is going to infinity. This is going to be going to the natural log of 4/3. So infinity times the natural log of 4/3 is infinity. And that diverges. So we're done with that one. Okay? take a look at number 144. They're really more like exercises in computing limits, aren't they? In 144, a sub n is 2 to the n plus 3 to the n over 10 to the n over 2. So again, let's rewrite this to understand it better. Okay, that's what the terms of my series look like. Okay. That 1/2 power on the n looks like a square root. So think about this. You've got 2 over the square root of 10 to the n plus 3 over the square root of 10 to the n. Okay? Take the limit. Since the square root of 10 is bigger than 2, and the square root of 10 is bigger than 3. This is a fraction less than 1. When you raise it to higher and higher powers, it goes to 0. The limit is 0. All right, so think about what the divergence test tells you in this case. You've calculated the limit of these terms, and they go to 0. What does that tell you about the convergence or the divergence of this series? Absolutely nothing. The divergence test only gives you a conclusion if the limit is not 0. Since the limit equals 0, we have no conclusion. From this test. Okay, and that's important to understand. Students oftentimes get into the habit where they think, well, if the limit is not 0, that tells me it diverges. And then they naturally might think if the limit equals 0, that means it converges. But let me show a simple example to you. That's our harmonic series. We know for sure, we should always know, this diverges. Very, very slowly, but it diverges, right? Apply the divergence test to it. Limit's 0. Okay, the limit of this is 0, but this diverges. When the limit is 0, you have no conclusion from this limit test. Okay? Don't ever think that because the limit is 0, that concludes that the test converges for you. It simply does not. Okay? All right. How about 146? That's a simple one. A sub n is cosine of n. Well, the limit of cosine of n oscillates, does not exist. So what does that tell you? If the limit does not exist, then this diverges. Which simply means the series does not settle down to a constant value as you sum it up. Okay? Doesn't mean necessarily the series is infinite. It just means the series does not have a single value. All right, now 148 is a little bit of a trickier one. A sub n is 1 minus cosine squared of 1 over n over sine squared of 2 over n. Okay, and this is going to involve just a little bit of trigonometry for us. Okay. What we want to think of here is, in the bottom, that's sine, there we go, sine of 2 over n times sine of 2 over n, isn't it? And that's sine of 2 times 1 over n. So think of the double angle identity for sine. The double angle identity for sine, sine of 2 times 1 over n is 2 sine 1 over n cosine 1 over n. Same exact thing for this. 2 sine 1 over n cosine 1 over n. So in other words, 2 times 2 is 4. Sine of 1 over n times sine of 1 over n is sine squared 1 over n. Cosine of 1 over n times cosine of 1 over n, cosine squared 1 over n. Okay? Now, one other trig identity to use is up in the top, the Pythagorean identity. 1 minus cos squared is sine squared. That's sine squared of 1 over n. And when we do the cancellation here of sine squared 1 over n from the top and from the bottom, you're left with 1 over 4 cos squared 1 over n. Now, take the limit. We'll do that over here. The limit as n goes to infinity of 1 over 4 cos squared 1 over n. As n goes to infinity, 1 over n becomes 0. The cosine of 0 is 1. So you get 1/4. If the limit of your terms of your series are not 0, we have diverges. All right, so quite a few examples there of the divergence test. Always good to be able to practice some basic limits. Now let's take a look at some of the exercises where we use the p-series result. Starting with 152. The prompt says, state whether the given p-series converges. Okay, so they're not expecting you to run the integral test here. They're expecting you to rely on your knowledge of the p-series analysis that we've done already. So 1 over the square root of n. Well, that means n to the half power. P is a half in this case. So recall what we concluded from the p-series. If I can find that page here. Here was our p-series analysis. P is bigger than 1. The series is going to converge. When p is less than or equal to 1, the series is going to diverge. 1/2 is certainly less than or equal to 1. So there's a series that diverges. Okay. All right. Let's take a look at 154. We have 1 over the cubed root of n squared. Cubed root of n squared is n to the 2/3 power. P is 2/3, less than or equal to 1, diverges. Very nice and easy test, isn't it? 156. We have n to the e over n to the pi. We want to write this as a p-series, so we want the n to be in the denominator. So think of this as n to the e minus pi, which if you flip it down is 1 over n to the pi minus e. Okay? The p-value is pi minus e, 3.14 roughly minus 2.7 roughly. That's less than or equal to 1. So this diverges. Okay. So now on to using the integral test to determine whether the following sums converge. And we'll take a look at problem 158. See if I can find another pen here. This one's starting to get a little bit dry. What am I going to do when all my pens run out? I won't be able to do videos anymore. All right. So in 158, n is from 1 to infinity, 1 over n plus 5. All right, so they're asking us explicitly here, use the integral test, nothing else, to determine what this is doing. Okay? So that means I'm noting that 1 over n plus, square root of n plus 5 is a positive expression. Therefore, I'm going to represent it with its continuous version. And then I need to just check a couple of quick things about this. I need to know that this is continuous and decreasing. Well, the discontinuity is at -5, so it's certainly continuous on the interval from 1 to infinity. And it's decreasing because the top's a constant, and so as the denominator gets bigger, this is decreasing. So that's easy enough to check. All right, so what that tells me is this improper integral is going to determine the behavior of this infinite series. And so I have to analyze this, and so of course we have to write this formally as a limit process to handle that impropriety of infinity. And then to handle this proper integral here that I'm taking the limit of, I'm going to do a simple u substitution. du dx is going to be 1. So this becomes the limit as b goes to infinity of 1 over the square root of u du, because du and dx are the same thing. Now, what about the limits of integration? Well, when x is 1, 1 plus 5 is 6, so u starts at 6. Okay, when x is equal to b, u is b plus 5. And so there you have it. Okay. All right, now let's evaluate this integral. This is the integral of u to the minus a half. So that's going to be 2u to the half when I integrate it from 6 to b plus 5. As b goes to infinity, you get the square root of infinity is infinity. So the series diverges, right? The improper integral diverged, therefore the series diverges as well. All right. Let's recycle some of this paper now. I'm going to start flipping these over. Let's take a look at problem 160. In 160, the sum is from 2 to infinity of 1 over n ln of n. And that's why they started at 2, because you're taking the natural log of the n. And if n was 1, that would be the natural log of 1 is 0. You'd get 1 over 0 is infinity. It would diverge at the very first term. You wouldn't have anything else to do. Okay? So again, we start at 2, oftentimes when we have natural logs in here, just to make it a more meaningful question to analyze. All right, so our continuous function, this is, after all, positive over 2 to infinity. So we can represent this as 1 over x ln of x. And this function is continuous on the interval from 2 to infinity, right? The discontinuities are at 0 and 1, not from 2 to infinity. And it's decreasing because the top's a constant and the bottom grows. So constant over growing means the ratio decreases. Okay, so sometimes when you have just a constant up top, it's a very easy analysis to see that. All right, so that means that this improper integral is going to determine the behavior of this infinite series. Well, that's the limit as b goes to infinity of the integral from 2 to b. And that handles the impropriety of the integral. Now for this, a u substitution. Let u be 1 over ln of x, du dx is 1 over x. So that means that du is 1 over x dx. 1 over x dx is sitting right here. So you're left with 1 over u du when you do the substitution. the limits of integration. When x is 2, u is ln of 2. When x is equal to b, u is ln of b. Integrate the natural 1 over u, you get the natural log of u. And when you plug in, you get the natural log of the natural log of b minus the natural log of the natural log of 2. As b goes to infinity, this becomes infinity, and the natural log of infinity is infinity, so you get diverges. Which is a little surprising, because when we look at this part right here, 1 over n, is the harmonic series. And what we've done to that harmonic series is we've made the denominator a little bigger, isn't it? We've multiplied it by the natural log of n, increasing the size of the denominator. And what we recognize about the harmonic series, it's right on the cusp of all the p series. So we know that if we were to look at 1 over n to the 1.000000000 as many times as you want, 1, that converges because the p is bigger than 1. Okay, that's only slightly bigger than 1 over n, isn't it? But it's enough to tip the harmonic series into the world of convergence. This amount here that I'm multiplying the denominator by is not enough to tip the harmonic series into convergence. So you think about the harmonic series as being right on the boundary between series that converge and series that diverge. That's true for p series that converge and p series that diverge. Okay, this certainly has a bigger denominator than a harmonic series, but it still diverges. That's something interesting to think about if you spend some time on it. All right, let's take a look at 162. 162, our infinite series, is of the terms e to the n over 1 over plus e to the 2n. Okay, these are positive, of course, so that means represent with this e to the x, 1 plus e to the 2x. And we need to know, is this thing continuous? Sure, it's continuous because the exponential function is never 0. Certainly never -1, it's always positive, so we're not going to get division by 0 here. What about decreasing? How do we know that that's decreasing? How would you determine that this is decreasing? Well, if the bottom is growing faster than the top, then the ratio is going to be decreasing, isn't it? E to the 2x grows faster than e to the x, so that's a decreasing. All right, so that means now I can represent the behavior of this infinite series by this improper integral. Okay. All right, now we write this as a proper integral with a limit. And now I have to figure out how to evaluate this. And the trick to this is to let u equal e to the x, but not this e to the x here, I'm thinking. It's this e to the x here that's being squared. This 2 times x is e to the x squared. Okay? And that means when I do my substitution here, this e to the x from the differential is the one up top. All right, so this e to the x dx forms the du. This e to the 2x is u squared. And the limits of integration I have here, when x is 1, e to the x is e. When x is b, e to the b is the top. And what is this? The integral of 1 over 1 plus u squared. That's our inverse tangent. So the inverse tangent of B minus the inverse tangent of E. Okay? And of course, this is the only one that is affected by the limit. The inverse tangent of infinity. You remember what the tangent function looks like when you graph it. Is this is where the infinity is. The inverse tangent of infinity is pi over 2. The inverse tangent of E is just the number. Okay, so this is finite convergence. All right, let's take a look at a few more of these ideas of the P-series. Take a look at problem 166. Express this as a P-series and determine whether it converges. So, the infinite series 3 to the negative natural log of n. So that is, of course, since that's a negative power, bring it to the denominator, 3 ln of n. Okay. Now the trick to this, and it is kind of tricky, I think. The trick to this is realize that 3 to the ln of n is the same thing as n to the ln of 3. Now, why is that? Well, if we take the natural log of both sides, we'll see. What does the natural log allow you to do? Bring the powers down. So you get ln of n times ln of 3 is ln of 3 times ln of n, which are, of course, the same. Okay, so that's kind of a tricky little thing here. But it allows you now to write this as n ln of 3. Okay. So what does that mean? Well, ln of 3 is your p, which is bigger than 1. So this converges. And that's the conclusion we get from this. Okay. 168 runs similar to this. In 168 we have n 3 to the negative 2 ln of n. Okay. So that is n in the top and in the bottom 3 to the 2 ln of n. Same reasoning we used up here. 3 to the 2 ln of n becomes, get this written out, n to the 2 ln of 3. Now what to do about this n up here? Well, that's n to the 1 power. You can bring it down by subtracting 1 from the power. It's the same base n in the denominator, after all. And so your p is 2 ln of 3 minus 1. And 2 ln of 3 minus 1 is bigger than 1. So this converges. And you're done with that problem. Okay? All right, now one last problem to show you. This is kind of a, think of this as an optional thing. This error terms that I talked about, and in this one problem that we're going to look at, 174, think of these as optional. These are just for your own personal interest, perhaps. I'm not going to be assessing you on the use of the integral test to bound errors on these for finite truncations of the infinite series. But let's do one anyways, just to conclude here. Okay, so a sub n is 1 over n to the 1.1, and we want our error to be less than 10 to the minus 4, or 0.0001. Okay, or if you like it this way, 1 in 10,000. Okay? Now, how do we do that? Well, the error, remember, the error is going to be bounded by the integral of n plus 1 to infinity of 1 over x to the 1 plus 1. So evaluate this. That's the limit as b goes to infinity from n plus 1 to b of x to the negative 1.1. Evaluate this by adding 1 to the power to get a negative 0.1. Divide by that negative 0.1, that's a negative 10, from n plus 1 to b. And so, let's see what this looks like. The limit, as b goes to infinity, of negative 10 times x to the negative 0.1, so that's a negative 10 x to the negative 0.1 from n plus 1 to b, negative 10 over b to the positive 0.1 when I brought that into the denominator, sorry. Minus a negative becomes plus 10 to the n plus 1 to the 0.1. As b goes to infinity, this goes to 0, and so you're left with 10 over n plus 1 to the 0.1 power. Okay. And I want this error to be less than 1 in 10,000. Okay, so multiply both sides by 1/10. I want this to be less than 1 in 100,000, so I want n plus 1 to the 0.1 to be bigger than or equal to 100,000. Multiply both sides by 10, or to the power of 10, and then subtract 1. N is 100,000 to the 10th power minus 1. That's how many terms you'd have to add up. That's like 10 to the 40th approximately, I think, in order to get the error in this sum. To get the sum of this to be, this finite sum to be within 1 over 10,000 of the infinite sum. That's what that's saying. Okay? All right, so again, I wouldn't want you to worry about these truncation error estimates from the integral test. Focus on, in this section, understanding the divergence test, the p series, and how the value of p determines the convergence or divergence, and then how to apply the integral test in general. Okay? All right, as always, if you have any questions or concerns, do not hesitate to contact me, and please work hard on your homework.